one of the concepts that we will use over and over again is that of the phase space. In order to understand the phase space, let's consider a pendulum of mass m and length L. The energy of the pendulum is given by the kinetic energy, which is given by m half times the velocity squared, plus the potential energy, which is given by m times g times the height of the mass at a given time. We see that the energy is given by two parameters which describe the system. First is the velocity, or phi dot in this case, and the other is the position of the mass itself, which is given by phi. The energy is a function of the momentum p and the space variable q, and because of its importance, it's obtained a new name, which is called the Hamiltonian of the system. Now on the left you see a solution to the Newton's equations of the pendulum. First in real space, where we just see the pendulum motion in x and y, but we could also view the same motion now in phase space, where we plot the velocity versus the position of the pendulum, and we see that in phase space it's a circular motion that is describing our pendulum. In the next step, we consider two pendula. The Hamiltonian of two pendula now depends on four parameters. It's the momentum and the position of the first pendulum, and the momentum and position of the second pendulum. So the Hamiltonian in this case is now in four-dimensional space. Now if we consider that these two pendula don't interact, that means we are looking for non-interactive systems, then the total Hamiltonian is given by the Hamiltonian of the first pendulum only, which only depends on parameters of the first pendulum, plus the Hamiltonian of the second, and with the parameters of the second pendulum only. Now, in the lecture Statistical Physics 1, we will mainly consider non-interactive systems, and those are called the ideal gas. Now, solving Newton's equations, what we can again do, we can look into the behavior of the two pendula in real space or in phase space, whereas in phase space we even have various possibilities where to cut through the four-dimensional cube, and on the left we see the phase space as we have it for 1 and 2, and on the right side we could, for example, look through a cut where we only look on the two positions or the two momenta. Now it becomes straightforward to extend our view for n particles. And let me remind you, in our case, n is typically a very large number, let's say 10 to the 23 particles. If we further consider that each particle is living in a 3D system, that means the phase space of every particle is 6-dimensional. Now we deal with a phase space for all these n particles, which is 6n dimensional. Now you see the importance of the phase space description, because a very complex system, even if it's containing 10 to the 23 particles, can be characterized by just a singular point in this high-dimensional phase space. There's yet an additional aspect of phase space, which is that phase space is quantized. We would zoom in at the origin of the phase space of our pendulum and look, let's say, with a microscope. We would at a certain time hit Heisenberg's uncertainty principle, saying that the product of delta p times delta q cannot be smaller than h. What this means is that phase space is actually not a continuous space, but it's made up of small blocks, delta p, delta q, which have the size of h. So phase space is quantized. Hence, as a wrap-up, phase space is an easy way to describe very complex systems, and we should keep in mind phase space is quantized in units of Planck's constant h.